So we thought we'd jig things up a bit by having a quick panel session. We're going to squeeze this into about 20 minutes, and we want you guys to be very engaged in the audience and have a bit of back and forth. We're really talking about the convergence. So it's an HPC conference with ISC, so we're talking about the convergence of HPC with AI. We kind of all have seen a bit of AI, maybe on the fringes, or maybe very deep, or maybe very advanced. So we're going to ask this expert panel about their opinions, and we want you to join in and offer your opinions. So first of all, please just go ahead and introduce yourselves. You've got like 1 sentence.
My name's Steve Sims. I work for Indiana University. I manage the high-performance file systems group there.
Tom Gibbs. I work for NVIDIA. I manage global developer relations with a focus on the convergence of HPC and AI.
Hi, I'm Stefan Gillich. I'm based out of Munich. I'm responsible for artificial intelligence and technical computing go-to-market in Europe.
Great, that was fast. So let me just open the audience up for questions before I start my little list here. Any questions? Case.
So, just an interest in what HPC industry do you see AI mostly used in? So, my background is I work for the Dutch tax office. We are more of an enterprise environment. You know, we're doing a large analytics infrastructure for analyzing tax data. AI is on the horizon for that as well, of course. So just finding patterns within tax data. What do you see as the industry that's of biggest importance in the AI that's for HPC?
Right, so which HPC current use cases, verticals, are the first to get into AI?
Maybe I can start.
Go ahead.
So one is certainly life sciences, right? I mean, you named it yourself. Wherever you have patterns to recognize, either in images or in speech or any other data, you can do that pretty well with using certain AI methods, right? I mean, AI is a wide field. You have classical AI, you have deep learning. You mostly hear about deep learning these days, but people tend to forget about the other thing. So in this area, right, when you have to analyze huge amounts of data and look for patterns on the one side and have a modeling approach, which, I mean, if you say HPC, I think you understand HPC as modeling and simulations, which many of us do. You can have a different opinion on that, but let's keep it like that. One example I can offer to you in life sciences is like with a big company, Novartis, we worked with just recently. They have huge images of cells, right, and they want to analyze on things in the cells, right, based on pharmacological substances, right, and they use AI to do that, right? So have huge data sets, lots of storage involved, and you have pattern recognition. On the other hand, you have a lot of HPC in that field as well, coming from the other side and say, I have a physical model where I want to model something and then do the numerical calculations to reach to the end. So this is where HPC and AI come together, right, and can help each other to have breakthroughs much earlier than with each one method, right? So you compare data you get from collecting a lot of data, right, and wisdom you get out of that with using AI, traditional analytics plus AI, and on the other hand, you do the modeling as well, right? There's other examples like in manufacturing, many people are speaking about the digital twin, which is basically a modeling of what these manufacturing industries have, right, and basically have a virtual copy of that, if you will. So that is also an area where HPC methods, modeling and simulation, as well as data analytics plus enhanced by AI come together.
Yeah, I think just to build on that, I mean, any one of the industries can have a use case for the application of AI. One of the things that I tend to focus on is that traditional HPC and machine learning can do a great job at detection and prediction, but in general, the turnaround time for getting your answer is well beyond the scope of real time. So if you wanted to implement something that you might have been used an HPC, traditional HPC modeling and simulation application to do, typically the completion time for that is going to be measured in days. And the operational execution is in milliseconds. And what we're finding is where scientists have been taking HPC simulations, traditional HPC simulations, using that data to train a neural net. Then they turn around and use the inference engine that comes out of that neural net, and they apply it to a problem that is executing in real time. One of the interesting examples is the LIGO experiment. And for people who may be familiar with that, that's the discovery of gravitational waves, won the Nobel Prize about 2 years ago. The detection of the gravitational waves using traditional machine learning is so computationally expensive that they can't do it on site. So they take the data, do a simple filter, and send it off into a grid. That's the way CERN processes their data as well today, because the computational expense is just too big to do it on site. What some scientists at NCSA did is train a neural net with a traditional simulation, an astrophysics simulation. The resulting neural net can execute actually more accurate and across more parameters of interest in milliseconds, and do it with a couple of processors, and they can do it on site. And what they're able to do, conceptually, and this is being studied now, is detect a gravitational wave in real time and signal optical telescopes to point at the point in space where the event happens. So you could actually see a core collapse supernova for the first time. Now that's pretty cool. But if you start to take it into industrial settings, the same type of thing can happen, where we can do some tremendous modeling and simulation in multiple industries, but going from that simulation to a real-time operational execution is really prohibitive. So you usually then have to leave the domain. Everything you did in the HPC then has to shift when you go into real time. So the coupling there, I think, is really interesting. Yeah.
Hey Sims, you're a quiet, shy, retiring character, and I think your microphone will work now.
Totally working.
Oh, wow.
Is this thing on?
So, working in the academic space, what I can say, the folks that we work with most often are doing computer vision work. There's a computer vision laboratory in Indiana. Those guys are on the machine all the time. We have a large informatics group. I would say that their interests are pretty wide-ranging. But really, it's the folks in the computer vision lab, I think, that are pushing our storage systems and our HPC machines the hardest.
Rich, your question?
Peter Jones' slide that showed like a third of the Lustre users are using AI. Were you guys surprised by that high adoption rate? Because I'm guessing 2 years ago that was 0.
Yeah.
I was surprised.
Yeah.
I was not surprised. We have been, we have within the company a group that's doing self-driving car studies.
Yeah.
And so we're sort of eating our own dog food in a real application area.
Mm-hmm.
And the I/O consumption is off the charts, absolutely off the charts. And the struggle conceptually is just getting the data in and out of the machine. It's the typical supercomputer turns a compute-bound problem into an I/O-bound problem. That's been true for 40 years. AI is like on steroids to turn it into an I/O-bound problem. So it doesn't surprise me at all, and I think that's only going to grow, because today, in many cases, people tend to constrain their HPC use because it's so computationally expensive to do ab initio modeling and how much data they might generate, because, well, we don't want to create all this data, because what are we going to do with it? It's out of the data storm and all that. Well, with AI, give it to me, right? I want all the data I can eat. The more data, the better. So I really think the challenge is going to be, where are you going to put it all? Well, I think the DDN folks have an answer for that.
Yeah.
But I think, as I look at the application of high-performance computing, the way the workflow is beginning to evolve, I think it's going to be dramatic how much more data is going to be generated.
Let's come back to that in a second. Case, your Dutch tax office, you said?
Yeah.
Have you got any aspirations, pretensions, or work in?
Yeah. So as a sort of a logical follow-on on what's happening with the analytics space right now, I think that's where we're looking at starting to apply AI as well. And it's something that's still started. So right now we're a fairly large SAS Grid customer, and we have a fairly large GS14K installed to drive all that. So I was also interested by the Lustre versus GPFS question. So I'll have more about that later. But anyways, that's something. It's definitely something that we're looking towards. And of course, as a tax office, we have a fairly large customer base in the Netherlands. And so also data to analyze, and that's definitely one of the areas is we're going to be applying AI in the future to work on that analysis as well. So it's a non-traditional HPC area, right? So it's an enterprise customer with all the enterprise requirements and everything. But this is it is an HPC cluster within an organization that has a lot of requirements as well.
Very cool. Pete, can you give us any insights into what you're doing at Sanger with AI?
Yes, so in the economics area, we've got past that equation. We've got large amounts of data. Everybody has that now, right? That's easy. But a lot of it's landlocked. If someone says they've got 100 petabytes of data, how do you access it? What do you do with it? It's kind of locked there. How do you gain the potential of going back and re-evaluating something new? But equally, you have new technologies coming through on the sequencing side. The original genome project took 10 years to come up with a draft of the first human genome, right? The next release of the sequencing technology, they're threatening us with 50 minutes. 50 minutes, and that's not just one genome. That's on one sequencer. Sanger doesn't buy just one sequence. You get the idea of what's coming through. These are about 2+ petabytes per year at the moment we're estimating per machine, with a downstream storage requirement of about 3 to 1 expansion of that. I don't know about you guys, but buying 100 petabytes a year to me seems quite an extraordinarily large bill. So looking at ways of analysing that on the fly, as GPU is an accelerated process, you want to stream that analysis, you want to collapse it, and AI seems to be an excellent workspace for this. We're actually seeing this also with various companies looking to do this on the instruments as well, to do the base coding, to do the QC, to do the basic analysis. So you can see this almost all the way through the stack, from gaining the data, doing the first pass of the data. What do I throw away? Well, there's no point in putting on disk if I can rerun the analysis in 50 minutes and increase the statistical certainty of that data. It's cheaper, faster, and better to just do it there and bin the rest. So we've kind of got our own SKA kind of equivalent. Our problem is our SKA is democratized. Anyone can buy these sequences. Anyone can have these sequences. That means everyone's going to have to look at a better way of analysing the data, because otherwise this becomes a fantastic scientific white elephant. So if you want to destroy a competition, buy them some.
So for folks, SKA is a square kilometer array. It's a radio telescope that I believe will be providing an exabyte a day of data.
There's other examples like that. I mean, somebody mentioned CERN before, right? We've engaged with these guys in the CERN Open Lab for quite a while, right? I know it for more than 10 years, and they always had this problem, right? Because they produce heaps of data in their detectors. And then what do they do with that, right? Which is the interesting thing in a huge sea of data, and this is where HPC and AI technologies come really together. I mean, they use traditional analytics and HPC modeling and simulation to do those breakthroughs, which you certainly have seen, right? What they did, and for them, I think it's a similar problem, right? They have lots of data, and they want to find the essence of that data, and even later on, because they've stored a good portion of that data, not all of it, obviously, because they do filtering as well, like you have said. But you can also sift through that data later on if you're looking for different things than you were originally in the first place, when they wanted to basically prove the Higgs boson.
So I have one more question, well, probably two. So like last year and the year before, we were talking about what can HPC learn from cloud, like Facebook-style cloud or Google-style cloud. I want to ask the same question about AI. What can HPC learn from AI, and vice versa? So what is it that HPC people do well that AI people aren't doing well today? And the opposite way around. Are AI people doing something that HPC people really don't understand?
Yeah. Well, let me take the first one. What HPC people always did very well is what I would say as scaling, right? So the idea of using multiple instances of a compute unit called a cluster was born to solve the problems in HPC. right, for high-performance computing. And that is something, when you look at AI, right, it's a inherently scaling problem, I think. And scaling that to clusters which are around at many of the HPC installations. I see a few of the customers sitting here, right? That is what AI can learn from HPC, right? How can we use similar infrastructures to basically get AI going together with HPC, because that's what we're going to see a lot in the research areas we have been talking about. You're not just using AI, you're not just using traditional AI, you use deep learning, traditional AI, you use analytics, you use visualization, you use modeling and simulation. And all that you want to support with a certain compute infrastructure, right? And HPC has been around for a long time, right? I've been in HPC long. I've done AI at university in theoretical terms. Now it kind of comes together because we created the compute to handle the compute you need for AI and advanced analytics and the data as well, right? So this is an area where we can learn each other from, right? But HPC was first in the high performance computing. If you say HPC is modeling and simulation, right, then it was invented. HPC was invented to do that.
Yeah. Steve?
Excuse me. I guess in my experience, I mean, having recently taken some graduate courses, my feeling is that the AI people could learn a lot from HPC in terms of workflow. You know, I guess my experience in laboratory is that everybody wanted they want their own system. But at least from the university perspective, that doesn't scale. You can't buy every laboratory, their own set of gear. So, I mean, when I look at the techniques that first came into play when I started in HPC, I guess like the open science grid, trying to scavenge cycles from all kinds of places. Excuse me. As we as a university build larger, faster, better systems, finding ways to batch process, I guess, jobs that I guess, the folks in the computer vision laboratory would like to do interactively, I guess I'd like to, and I found myself doing this, taking some folks that had done HPC for years and put them in a room with young students and have them sort of trade ideas, where, one guy, hey, you got a DECnet cable? I could really use a DECnet cable. It was just interesting hearing him sort of explain to students kind of, where he had come from, and different ways of thinking about processing. Anyway, so from my perspective, again, as an educator, youngsters could learn a lot from what's been going on for a long time.
I think I'll build on both comments. I'll go back to the real-time application. So one of the things I think that HPC obviously offers, because of the 40 years of history with modeling and simulation, is a clear understanding of the first principles model that drove the answer. So you can take the answers that you get from an HPC simulation and tie them back to first principles, what you drew on the whiteboard. And that's really cool, and that's super powerful. But you're never going to get that simulation to run at anywhere near real time. That kind of performance is just not possible. And as the technology roadmap is generally slowing down with Moore's law, the pace that we've seen for HPC, where about every 10 years you get an order of magnitude performance gain. We go back to the kind of the beginning of supercomputing and track that gain. You've probably seen about 4 or maybe 5 orders of magnitude improvement since the first craze. Well, what we're seeing with the early implementations of AI is that the trained inference engine is 6 orders of magnitude faster than the simulation. It's hard to get your head around. I mean, you're basically, when you move from the simulation to the AI-enabled inference engine, you're outpacing the entire, in 1 year of analysis, you're outpacing 40 years of gain in terms of performance. And we're only at the beginning. So what you can do, I mean, actually, I think that's where things are going to get really exciting. When you can get 6 orders of magnitude performance gain, and then you get maybe another 2 or 3 orders of magnitude, you know, many of the simulations measure things in nanoseconds per day. Well, now you might be able to measure things in nanoseconds per second, or maybe nanoseconds per nanosecond. And when you get to that kind of performance, it opens up things we haven't even thought about trying to do with modeling and simulation. And I don't think you can ever uncouple them, because whatever you're doing with AI, you're not going to be able to tie that answer directly back to the first principles. So you have both things working together. So maybe you're doing something in an incredible new capability with the AI inference engine, and then you go back and you're checking what's been happening with the ab initio modeling. And I see the two things as being very synergistic and opening up new potential here. It's going to be exciting, I think, in the next 5 years.
And last question, but definitely not least, audience can ask more. What's the impact of all this on storage, I/O, data, managing data, life cycle of AI data? What do you think the impact's going to be of AI on people like us and people like you who manage these large storage systems?
I need more ions. I mean, like just a crap load. I mean, I think that when I look at my history in storage, you know, it's gone from I need more streaming performance, and now when you look at people who are going through testing phase, you know, I've got my zillion cases, some of which are, you know, 1K, and I need to plow through all of this data. They just can't get enough IOPS. And, you know, my metadata server, you know, the one that I have right now, and am luckily going to be replacing soon, it's ready to cough up a hairball, because it's just overwhelmed by all the demands.
And the IOPS need to be really fast. I mean, they can't be fast enough. Again, this kind of performance gain that I mentioned, you got to keep up with it. And you know, the idea of, you know, as you were saying earlier about, you know, flash, the low latency speeds that you can get from the new drives, I just think, you know, it's more IOPS and faster IOPS.
Yeah, well, there's not a lot to add, but we need to do it. I mean, AI lives on data, right? There's only a little bit of AI without data, right? And deep learning certainly lives completely on data. So you need to ingest the data, you need to store it, you need to pre-process it even before you go into the training steps. There's lots of things to do. So the data hierarchy on every level, I think, is going to be challenged, right? And we need to do a lot on technology, right? SSDs, we have Optane technology, right? And lots of storage, baseline technology, and then you put the software layer on, and I was talked about things here. So all of these things need to work together, right, with the compute side as well. But it's very clear, right? You need to get the data in fast, right? And you need to process it fast, right? And there's lots of technologies around that which are key for that.
Great points. Case, one more?
Yeah, there's one of my favorite points is that always you have these, you know, incredibly fast compute boxes, the DGX1 and so on, eating a lot of data. Yeah, then you have these incredibly fast storage boxes. And then there's a network in between, or a fabric, or that's going to be, and I see very little spectacular development in the network fabric area compared to what's happening on both ends. And so that little piece in the middle is going to remain a weak point.
Are you setting me up for my presentation?
Oh, are you? Okay, well then thank me later.
Actually, the key thing to your question is really, if I may, you need to have a balanced system. Right? It doesn't help you good in one thing and you don't get the data in and out, right? And and vice versa, right? So the compute side, the networking side, the storage side, it needs to come in a certain balance. Obviously that balance is different also from, if you look at some HPC applications which don't need a lot of data, right, that's different to a deep learning application which needs a lot of data in jest, right? So you have that variance of applications, and coming back to what I said in the beginning, right, what you're looking for is systems which can actually do that in a balanced way, and give you the required performance on each level, not just on the compute side, but also on the I/O side.
I was going to say, to build on that, I think a big change you'll see in HPC systems in the next few years is going to be partitioning, because the kind of, whatever fabric attached technology you're going to want to use for the part of the system that's doing the training and whatnot, is probably going to be expensive when it's all done. And you may not want to proliferate that on every single node in your system, because the HPC side of the system probably doesn't need that much I/O. And if you try to compromise and have everything be the same, which has generally been the norm in HPC systems, you'll either overbuild for the HPC side, or you'll starve the AI. So I think you're going to see much more partitioning of the systems. It'll be kind of tailored to the different parts of the workload.
Last comment, Sims?
Well, I was just thinking about this notion of partitioning. I mean, we do poor man's partitioning by having, separate machines for separate jobs, but I can totally understand where you're coming from, in the sense that I remember early on giving a tour of the machine room, and Professor Mookie Bake was there, and he was explaining to his students. He said, well, this fabulous machine here, half of the cost of this machine is for a high bandwidth, low latency interconnect that none of you will ever use. And of course, 20 years later, that's all he does is use the high speed, low latency interconnect. So, I'm curious to see where networks are going to go.
Cool. Thank you very much, my panel. Stefan, Tom, Sims. Thanks very much.